This is an A-level AQA chemistry question on the topic of equilibrium and more specifically Kc. So pause on each section, try to answer them and then review once you're done. So here's parts A and B. And here are parts C and D, taking you to a total of 8 marks. So taking a look at the answers now, we have acid X reacting with methanol to form an ester Y. And we can see we've labelled those two species as X and Y, which is what's wanted in the expression for Kc. Now, when you write out the Kc expression, you've got to remember a couple of standard procedures. One is that you have product over reactants, and two is that you represent concentration in moles per decimeter cubed by putting the species in square brackets. So what we have is this. Now, some people might not read the question properly and put the full formulas of X and Y in. Read those questions carefully. That was not needed. Then we move on to part B. And we've got a mixture of 0.32 molar acid X, 0.84 molar methanol, and they're allowed to reach equilibrium. And at equilibrium, we had 0.26 moles of ester Y. We need to use that data to find out the remaining equilibrium moles. And I would always tend to draw out the table, as I've done here. I've written it out and I have put in the 3 figures that we have. So we know our 2 initial moles and we know our equilibrium moles of Y. Now from there, we're going to take a look at the initial moles of the product, and they are going to be 0. We don't start with the product. So nice and simple to begin with. For the next thing, I'm going to take a look at the H2O. Now, to determine this number, I am looking at in the equation, when I make 1 mole of Y, I make 2 moles of water. I didn't make 1 mole of Y, I made 0.26. So I'm going to make double that amount of the water. What I'm then going to look at is the X, which is a 1-to-1 ratio with Y. 1 mole of X makes 1 mole of Y. So 0.26 moles of X makes 0.26 moles of Y. So that means I've used 0.26 of my initial 0.32. I've got 0.06 moles of X. And finally, looking at my methanol, I'm actually going to compare this with water, because that's a 2-to-2, or therefore a 1-to-1 mole ratio of methanol to water. So if I've made 0.52 moles of water, I needed to use 0.52 of the 0.84 moles of methanol. And that leaves me with the 0.32. And I've then substituted those figures in down at the bottom. Moving on to part C, calculating the value of Kc and stating the units. Now, I've brought a little bit of information over again. You would have access to this in your paper. I've brought over the amounts so that you can see where they are coming from. And I'm going to substitute those figures in to the expression for Kc that I've also transferred over. Now, you'll notice I've put the number of moles in. I've not put concentration. But actually, because this is a calculation that leads to Kc having no units, what that actually means, or what happens alongside that, is that the 1 over V in each of the concentrations fully cancel out. So for that reason, the volume here is not necessary. Once I've substituted those figures in, I get a Kc value of 11.44. Now for part D, we have the enthalpy change that was given right at the beginning of the question that I've brought over again. Predict the effect on Kc if the reaction is carried out at a lower temperature. Now this is a one-word answer, but I'm going to go through the explanation that underpins it. In the first instance, we know that a lower temperature will favour the exothermic reaction. And we know the forward reaction is exothermic, because the delta H is negative 15. So that means at a lower temperature, the equilibrium shifts to the right. Now that means that we've got an increased concentration of products, a decreased concentration of reactants. So if I then look at those numbers within the expression that we have, that means that Kc is going to go up. That takes us to the end of the question. Thank you for listening.